Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 29, and we are going to discuss a two-way factorial ANOVA, and this is chapter 5 in our textbook. So let's get started. We're using an RMD file, as we do in this class, and I have some information up here. You're, of course, allowed to change what's in green here in the quotation marks. Please do change that. But once you get to line 5 here, do not change. And please don't change this first chunk or the second chunk. We'll run these. And then we're going to get into the experiment, the example. This is a battery experiment, and so I've got some information, general information that wouldn't be in a homework or what have you. You want to remove this. But we're talking about the simplest type of factorial designs only have two factors or sets of treatments. There are A levels of factor A, B levels of factor B, and if we replicate, there are going to be N replicates for each of these combinations of A and B. There's going to be A times B treatment combinations, and within those there are going to be N replicates. So same way of saying it, but just a little different. So we're going to have two factors here, and we have an engineer who's designing a battery for use in a device, and it's going to be subjected to some extreme variations in temperature. So the only design parameter that he can select at this point is the plate material for the battery. He has three possible choices, and they don't tell us what those choices are. When the device is manufactured and shipped to the field, this engineer has no control over the temperature extremes that the device will encounter, and he knows from experience that temperature will probably affect the what we call effective battery life. But the temperature can be controlled in the product development laboratory for purposes of the test. So we're still interested in that, and then we can communicate to the users that what the battery life should be in these three different temperature levels that he's choosing. He's choosing 15 degrees, oops, that's not showing up well. He's choosing 15 degrees Fahrenheit, 70 degrees Fahrenheit, and 125 degrees Fahrenheit, because these temperatures are consistent with the in-use environment of the product. So there are two factors. I don't know why I said because, but there are two factors, each with three levels. Okay, this design is sometimes called a 3-squared or a 3-2 factorial design. Okay, because it's 3 squared. So we have 3 of one factor, 3 of another. 4 batteries, n equals 4, are tested at each combination of the plate material and temperatures. And we have, so this is 3 times 3 times 4 equals 36 tests that are run in random order. That is one of the drawbacks of a full factorial model, is that it requires a lot of tests, so it can be expensive. So in this problem, the engineer wants to answer the following questions. What effects do material type and temperature have on the life of the battery? Is there a choice of material that would give uniformly long life regardless of temperature? Okay, so those are some pretty good questions. In fact, the last question is very important. If it's possible to find a material alternative that is not greatly affected by temperature, then we should do so. The engineer can make the battery robust, in this case, to temperature variation in the field. And this is an example of using statistical experimental design for robust product design, which is a very important engineering problem in general. So again, we have factor A will be material, factor B will be temperature. Again, A equals 3 levels of factor A, and B has little b equals 3 levels. And each of the A times B, which is 9 combinations, are replicated or repeated n equals 4 times. So we have our data here, and I won't spend much time on this. This is really not any different than before. What we did change was, instead of having a calculation here like you could with a one-way ANOVA, we really can't do that. So I've just put in places for you to enter A, B, and N, and then N, capital N, can still be calculated. So let's go ahead and run this. And now we have our table, and again, I do want you to put this table in all your homework and projects. Oops. So, descriptive statistics. So we ran the descriptive statistics here, and I did this 3 different ways. Here's by the material type, here's the operating temperature, and then here is by the combinations. Now, what we're going to do is we're going to test factor A, the material, we're going to test factor B, the temperature, and then we're going to test the interaction term between type and temperature. If the interaction term is significant, then we're not interested in just the material or just the temperature. We have to be interested in combinations of the material and temperature. That's the only way we can discuss it if interaction is important. So, by looking at these, I've done descriptive statistics. I have analyzed each of these. I've talked about the range of the values. Say this is for just material type here in the first paragraph. The range of the values so the battery life, medians. This is the median, sorry. I started with the median. Then I talked about the means. I talked about which the highest mean, and in this case both are the same, associated with material type 3. The lowest of both happen to be associated with type 1. The medians increase across the types of material, although we don't know what these types of material is. There may be a chemical composition that increases across the types or decreases across the types. We don't know with what's been given to us, but there may be a reason for that. Or it may just be a random occurrence that these were randomly named 1, 2, and 3, and it just so happened that that happened to be the order in which things change. But since it's a categorical variable, we can't be saying that as material increases, that's not what you can say, because it's the type of material and it's randomly assigned 1, 2, or 3 as far as we know. So the standard deviations range from 35.8 to 49.5. And I put in parentheses which those are. Okay? And then I talk about for operating temperature, I do the same thing. And I did not analyze the interactions here, but we could, but that's a lot of writing. So unless there's something in particular that we notice, it's going to be hard to analyze this and summarize this. So I think it's better to look at these two, but we do need these means for the combinations later on. And then exploratory graphical analysis, you're free to choose the one you think tells the best story. I think that the box plots usually tell the best story, but not always. And so I have analyzed the box plots. We'll run those and let's see what we see. So here's by material type. Here is by operating temperature. Oops. And then I could do one by the combination, I believe. So we will do figure 2B, and we'll say battery life by material and operating temperature. I'm going to hit enter there, and then there, and I'm going to go, let's see, type plus temperature. And it gives us all of them. So it is important. I'm going to leave this in here for you so your copy will have this. So you can see the first, before the period is the material, so type 1, type 2, type 3, and this is doing it by temperature. Okay, so this is keeping temperatures all together across the materials. So I think that I will reverse the order here. That might help me because it makes more sense for the material to go across the so to keep the material constant and change the temperature, doesn't it? So that's what we've done. We reverse the order, and that leaves 1 is the material 1, 1, and then 2, 2, 2, and then 3, 3, 3. So we keep each type of material together. You can kind of see what happens. Interesting picture. Again, we'll run all 3, so we have all 3 here. And then we have a dot plot, and whoops, oh, I said not to include these, so I'm going to, because you'll include one, not the other. In this case, I didn't think that the dot plots gave us as much. When I look at this, I can't tell what's happening between them. I can tell a little bit, but not a lot. That's the material. Here's the operating temp. We can tell that it's as the temperature increases, the life decreases, it looks like on average. And now we're ready for the ANOVA. And so I've put the ANOVA here. I've put 3 different ways to do the ANOVA. Instead of using the method that we've used before, which is this third method, I decided to use a linear model. Okay, and so we've got life by temp, or type by temp, and then by type colon temp. Okay. Now in the other way to do this is temp times type. Okay, instead of the colon. That's another way to do it. And same linear model, LM object, or AOV, we would do this, and I think the asterisk works there as well. Okay, so we're given an Anova table here. Type is across here, it's significant. Temp is significant, and look at this, interaction is significant as well. So when we start, we can't just talk about the type of material by themselves, and we can't just talk about the temperature by itself. We need to talk about what happens across for each material type across the temperatures. Okay, that makes the most sense, and so that's what we'll do. So I'm going to do the test for all 3. I've written them up. I want to point out that for these, because we have this model, it's important to assign, we have more than one factor, it's important to tell the reader which one is which. So in this case, I said that tau I added this, tau I is the treatment effect for the ith material. So now we know that tau goes with material, beta goes with temperature. Okay, and then I have tau beta is the interaction effect for the ith material and the jth temperature. So I've added that to the ANOVA up early here. I'm not putting it anywhere else because it is messy and it's a lot for the reader. So we say it once and that's good enough. But we will repeat the model, but just not this extra description of, from here to here. See, that's a lot of extra to give the information. So we'll do that for the ANOVAs, but then you don't have to do it in this class for the rest of the test, okay? So save you a little bit there. And so we have a test statistic given 7.91, 2 and 27 degrees of freedom. Be careful with that. Remember that we want the 2 degrees of freedom for type, but then we want the 27 for the residuals. Please don't divide by 4 or use 4. It's not. It's 2 and 27. And for temperature, it's going to be 2 and 27. And for type, temperature for the interaction is going to be 4 over 27. Okay? All right. And so we see that the p-value is approximately for the material, 0.002. We reject. There does exist. And then I say for 12 observations, B times N. For each level of A, there's going to be B times N observations. You can look at your data and see this if you want to verify. So here I have from material type, I have 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12. So for every material type, there's going to be 12. By the way, for every temperature, there's going to be 12 as well, because it's 3, A is 3 and B is 3. Okay, so we got 1, 2, 3, 4 for 15. For 15 here, we have another 4, that's 8. And then we have another 8, that's 12 for 15. Okay, so I've written this up with the multiplication so you can figure this out each time without counting, if you like. So this was with B, for factor A, you multiply the remainder. B times N is 12. For factor B, I won't go over this one. You can read it for yourself. A times N is also equal to 12. And now for the interaction, since it's significant, this is the most significant thing we're going to put up here. So we have, after the model, the test statistic is f of AB is 3.560 with degrees of freedom 4 and 27, corresponding to a p-value of 0.0186. We reject H naught. There does exist sufficient evidence to support the claim that the interaction between material type and operating temperature is different than 0 for at least one ij in 1 to 3. Since they're the same, I can do it this way. If A was 3 and B was 4, I'd have to say I in 1, 2, 3 and J in 1, 2, 3, 4. Okay, so I'd have to say it separately. But in this case, little a is equal to 3 and little b is equal to 3, so I can combine them. Okay, so for the IJ material combination at a 95% confidence level, the test was performed using a two-way fixed effects ANOVA with n equals 4 observations in each material type and operating temperature combination. Okay. Now, model adequacy verification, it's exactly the same. I'm not going to spend your time going over this, so I will say that I did exactly the same format here that I did in Chapter 4. So we're going to analyze equality of variance. We're going to use the residual versus fitted values plot, the scale location plot, and then the leverage plot. And then we're going to, I've put in here the Levine's test, even though it really wasn't necessary looking at these plots, but I did put that in there for you. So please read through this and see the Levine's test. So if you have no doubts that the assumptions are met and the question doesn't tell you to do Levine's test, you could remove this. Okay. And then we're going to do normality. If we look at this QQ plot, it's great. There is no question about normality. But I did go ahead and do the additional QQ plot with the confidence bands on them, and I also did the Shapiro-Wilk test for normality, even though there was no need for it. And I've written that up and included it here for you as well. We also checked the independence assumption across time. So here's the Levine's test. You can see it's great. Here's the, I need to run these though. I haven't run them. They're just sitting here from the last time I ran this. So let me make sure the code is run so that the information is in memory. And so you can see there are no points outside of the line here, the bands here. The Shapiro-Wilk normality test, P is 0.61, so no issue there. For the independence, the largest number of values on either side is 3, and that's not large enough for us to say that we have this positive correlation. It's just 3 here and there, not all the time, and we'd really want to see like 5 or 6 or more repeated back and forth to say that there was a positive correlation. Okay, so none of the assumptions are violated. It's all written up there for you. Now, point estimates, I left that out in Chapter 4 and Chapter 3, Chapter 3 and Chapter 4, I believe, and so I should not have. So I've entered it here. It's a little more complex. So what I've done to make this easy is for mu I hat, that's the means for material types. And so we took that from Table 2. And then the operating temperatures, up in the descriptive statistics, that came from Table 3 up there. So I just typed those in. And then to make this easier, since there's 9 values for the interaction effects, I just went ahead and put for I equals 1, so the first material type, across the temperatures, I put the means. And then I did the same thing for the second material type, and then the same thing for the third material type here. And then I've calculated the treatment effects using, I just typed these in and then did the calculation. So you'll have them. The only problem here is if you have more than 3 levels of I, you will have to modify this, okay? So it will flex for you for different values of Actually, you know, there's going to be a problem if you try to print the tau i's, if they have 4 here with the beta j's, if there's a, let's see, no, so I is 3, so if I was 4, then this would be fine. Okay, yeah, so this actually is flexible, so you can modify it so that it prints out these values. And so some of the problems probably ask you for that, and so I've put how they're calculated here. You'll want to take this part here out and delete it when you turn in your homework. There's no need to say that. That's for you, so that you know how to do this, okay? So this is for you, your information, but delete it when you turn it in, please. Delete that part, okay? So there are the estimates, the treatment effects. Those have to be calculated. And then we have pairwise contrast for Shapir's method. We're going to do that. And so the first thing are hypothesis tests, if you're asked to test. So we would do this. So since interaction is important, that's the only thing that we should be testing here. We should not be testing just between different materials. We should not be testing between different temperatures. We need to test the combinations only, okay? Now, I have done that, and I've run this, but to be kind, so here are what you get. When you run this, you get, here's the type. So here's the differences between 2, 1, 3, 1, and 3, 2. And then temperature. So it gives you those. But again, if interaction is important or is significant, not just important, it's significant, you ignore these first two and go right to this temp, type, and temp here. And you look for which ones are significant. This method gives you the dot, the asterisk, double asterisk, and it gives you the codes for what each means. And that's what I've done. I've separated those up by how significant they are. And so, oops, sorry about the display there. So for interaction, here I've given you the test, the hypothesis, and then for the actual significant differences, here's the first one with p-value between, we didn't have any 3 asterisks, so I started with the 2 asterisks here, and I put them all together, so between 0.001 and 0.01. And so I put them as combinations. Material 1, temperature 70 degrees, and material 2 and 15 degrees. Now, if you look at this, you'll see some other significant, oops, where did it go? All right, so where did it go? Okay, so yeah, okay, it is still here. Now, if I see the same number, 1 here, it doesn't matter if this is significant or not. I ignore it. That's not an interaction because they're both in material 1. So that's a difference in temperatures, the main effective temperature. So we're not interested in that. These numbers, these material types have to be different, or the temperatures have to be different. You know, so you don't want 2 and 70 and 3 and 70. Well, that's a difference in material. So again, we don't want that. So we want to have a different material and a different temperature. We want to look at those combinations, okay? So I've listed those out. I've written them up for you here as interaction. Now, because you may not always have an interaction effect that's significant, I've also given you the write-up for material. Again, you would only do material if the material effect is significant. And this is material type, I guess I should say, because I called it type in the I just called it type in the table or in the data frame. But for material type, you only do this if material type is significant in your ANOVA and interaction is not. But again, I say this does not apply because interaction is significant. So we would not turn this in. The same thing with operating temperature. You only do this if 1, operating temperature is significant according to the ANOVA, and 2, interaction is not significant. Okay? So in our case, interaction is significant, and so that's the only thing we should write up. Okay. Then if you're asked for specific, or if you're asked for to interpret specific confidence intervals or an interval, this again is how you need to do it. Correct notation, the correct format, and it's carefully said so that it's technically correct, theoretically. Now, the next one we did is pairwise for Tukey's method. Okay, so the same thing is true. We're only going to look at interaction because interaction was significant. If it's not significant, then you'd get rid of this area with interaction, and you would only do whatever main effects, the material or the operating temperature, or both, that are significant according to the Anova. All right, so I've written all this up for you so you have it. And again, I've given you interpretation for the confidence interval if you are asked for that. All right, and then the code, and you'll see that I've broken this up so it looks nice. Here's for the material. So material, here's for operating temperature, and here's for interactions between material types and operating temperatures. All right, that's it for this video, or the content. Now I want to spend a little bit of time talking about how to knit this. I know that some students are having trouble knitting, so you don't have to save. When you knit, it will save it for you. Okay, so what we do is we knit to PDF. Now, this comes to a different tab down there. This is the Markdown tab. And it goes through this, and in this case, I didn't run into any errors there. You see that the red over here, the red stop sign, is still going. If there is an error, it's going to crash, and it's going to give me some things in red, just like this. All right, and so it's important to scroll up. Okay, so this tells me about a new version of Text Live, all right? And then it tells me that. And now it says illegal, here we go, illegal unit of measure, point inserted, to be read again. And this, and then it does some stuff, relax something, but here is the important part. I have done V-space and I forgot to put a unit, millimeters. So what I'm going to do is I'm copying this, and I come up to, I'm going to pretend like this is not open. I come up to edit, or I click find, or I can say Control plus F, Command plus F for those. I'm going to paste in here, and now I'm going to find it. And so I need to put millimeters in there, and I'm going to see if I can find no more occurrences. So I'm going to knit again to PDF, and I don't have to save. You notice it just saved it. So that's not an issue. And so now it's output file. All right, we did it. Okay. So it's important, if you get an error and it says execution halted, it's important to scroll up and try to find something that's actually in your text. Search for it and replace it. The other thing that you can do is you can knit this to HTML. It's a lot less stringent requirements to do that. Many times, if there's something wrong in these dollar signs here, it won't knit to PDF, but it will to HTML. And so then you can just, oops, what happened to it? Here it is. So then you can look through here and see, you'll notice that the math is bigger and kind of italicized. So you can look through, that's the first place I'd look. I'd look through the math and see if there's something that doesn't look right. And if you find something that just doesn't print out right and there's garbage or errors, then you can go see where it is, go try to fix it. My cat Pippi is trying to get my attention and tell me that I've spent enough time on this video. So I will listen to her and let you get on with the rest of your day here. But I did want to show you this, that you can do the HTML, look through it. If you can often find the problem, if you're looking through it, sometimes it jumps out at you when you're looking at these. Sometimes it doesn't, sometimes it's subtle, but if you've got that error, then again, you'll probably be able to knit it to HTML even when you can't knit it to PDF. And if you're in a crunch, you can always print this as a PDF, or let's see, so right click, oh no, how about Control P? Oh, I'm not in the right thing. So if I open this up, let's see, I need to go to where it is, and I think it's going to be under code. And this is chapter 5, and I'm looking for HTML. Here it is, today's date. And so I could, print, choose save as PDF. It's loading the preview, and print it that way to PDF. So that's one way that you could do this and not get points taken off for it not being a PDF file. All right, that's it for this video. I hope you've enjoyed it. I hope it's useful. Please make sure that if you have questions, come to office hours. If it's code, I am happy to walk through your code with you and help you debug it if necessary, or answer some questions. If you need help before then, you can email me. If it's about code, you'll need to send me your code file and tell me where you're having the problem. Don't just send me the file and say fix it. I probably will not do that. It's going to be an interactive effort so that you learn. But I am happy to help you. Please take care of yourself and stay safe, because we hope to see you next time.